Welcome to the 18th video of Quantum Mechanics Done Right, the shortest path from novice to researcher. In this video, we're going to talk about the third part of the book, which is Advanced Quantum Operator Methods. When we talk about advanced methods, a lot of these are applications. This section has 11 chapters, and we're going to develop a lot of advanced ideas, particularly ideas that take us from looking at single particle quantum mechanics into many body physics and multiple particle quantum mechanics, where things change quite a bit in going from one to the other. We start with time evolution. Time evolution being one of the more challenging aspects of single particle quantum mechanics, especially when the Hamiltonians depend on time. Then we'll discuss a more complicated spin model, the Heisenberg exchange model, which is more complex than the Ising and XY models. And it doesn't have an exact solution via fermionization, but it does have an exact solution via the beta ansatz, and we'll talk about that. Then we'll get to the Dirac equation and relativistic hydrogen. We'll talk about bosons and fermions. We'll talk about the Hubbard model, and we'll do some applications to chemistry. The Hubbard model is a characteristic model of strong correlations for electrons that are in lattices, and it has applications to solids, especially magnets and high-temperature superconductors and other strongly correlated materials. We then will quantize light. We'll describe how you can do quantum simulation with ion traps. We'll examine decoherence. And then finally, we'll conclude with a chapter on real experiments on single quanta. The first chapter is on advanced mathematical techniques that we're going to need. These are mainly techniques involving matrices, so we will talk about the trace, we'll talk about the determinant, we'll talk about positive definite matrices, we'll look at functions of matrices, the Perron-Frobenius theorem, and what a partial trace is. We will also discuss how you can sum many infinite series just by using the geometric series, because the geometric series allows us to sum exponentials, and many of the infinite series that we're going to need involve exponentials, so we'll discuss how that works. Most of that is required for doing some of our time evolution. And then we have a concluding section where we discuss the Born rule as being essentially a fundamental rule associated with probability as opposed to being a postulate. Again, this isn't a proof, it's more of a motivation than a proof, but it's a pretty strong motivation for why we have the Born rule in determining the probability when we work with quantum mechanics. Next up is time evolution. Rather than working from a time-dependent Schrödinger equation, which is a differential equation, we instead use properties of unitarity and the semi-group property of time evolution to motivate the Trotter product formula for time evolution. We then use that to describe magnetic resonance, and here I really like the way that this works. It makes the analysis for magnetic resonance much clearer and cleaner, I believe. We then will discuss time dependence in the harmonic oscillator, including how coherent and squeezed states evolve as a function of time. We'll look at the free expansion of a Gaussian wave packet, which is related to what happens with squeezed states. We'll look at the interaction representation, which is a common method used, especially if you want to expand your time-dependent perturbation in a power series. We then will talk about the Landau-Zener problem, which is one of the most interesting and really challenging problems to solve, even though it only involves working with a two-state quantum system. We'll look at the driven harmonic oscillator, which is another really nice problem that can be solved exactly, but it's a really complicated problem to work through. We'll then look at photoproduction of hydrogen. This will help us explain what the sharp lines are in the spectra, and we'll also be able to calculate what the lifetime of the different states are. And then we'll look at a stroboscopic relationship between the XY model and the Ising model, and this is a technique that was used in ion traps to simulate the XY model. We then will discuss exchange and the Heisenberg model. Exchange is a truly quantum concept, and it is essentially a force that arises from the fact that quantum mechanics must be indistinguishable for indistinguishable particles, so that when we interchange two particles, the properties of the system have to behave in a certain way. We discuss in a lot more detail how that works with bosons and fermions, but for spins, exchange is the most prevalent quantum effect, and it leads to magnetism typically. And the most simple way to describe that is either with a ferromagnetic or an antiferromagnetic Heisenberg model, and we'll describe in detail exactly how that works. There's a very important result that was worked out in the 1950s for the antiferromagnetic problem called the Marshall sign rule, which governs a lot about the properties of the solutions of these systems. And then we'll really get into the nuts and bolts, and we'll show the beta ansatz solution to the 1D Heisenberg model. This is one of the most complicated calculations that we do in the book, but it's really cool to see how you can put all of the many body physics together, similar to the way that we worked with single particle quantum mechanics, and find energy eigenstates in the one-dimensional problem. Then we move on to relativistic hydrogen. For this, we start with the relativistic Dirac equation, which we'll derive. And then we'll look at the energy eigenstates of hydrogen using techniques very similar to the factorization method that we used for the non-relativistic case. It takes a bit of massaging to get the Dirac equation to look like that, and that's actually most of the work that we have to do. Then we'll look at the wave functions of hydrogen. This is a lot more complicated calculation, so we won't work out the wave functions in general, just the 1s, 2s, and 2p. This is mainly because we have to work with what are called Dirac four-spinners, and we have to get the shape of the four-spinner right, and that actually takes quite a bit of work. And then we'll discuss the fine structure which is present in the spectrum, and then things that go beyond the Dirac equation, such as the Lamb shift and the G-2. Then we have a chapter on bosons and fermions. Quantum mechanics requires states to be symmetric or antisymmetric as we interchange particles, and we'll talk about the consequences of that. We'll learn about photon bunching, which is a property of bosons. Bosons like to stick together. We'll discuss second quantization in a more general form than the fermionization that we had introduced earlier when we talked about spin models. We'll discuss how you can work with fermionic states. Then we move on to the Hubbard model. This is the hydrogen model of solid-state physics, especially strongly correlated solid-state physics. We'll start by talking about the symmetries, which include both spin and pseudospin symmetry. Then we'll look at exact diagonalization. There is no known exact solution for the Hubbard model, except in the one-dimensional and the infinite-dimensional limits. But both of those solutions are sufficiently complicated. We're not going to go through the details of those in the book. But we can solve it for small systems, and by looking at the solutions for small systems, we get a lot of insight into how the model works. We'll then prove a very important theorem called the Nagaoka theorem, which tells us about ferromagnetic solutions when we remove one particle from a half-filled band. We'll then discuss a very important technical result called spin reflection positivity, and how spin reflection positivity can be used to prove important results about the Hubbard model. And that will lead to our discussing Lieb spin ladders and Lieb pseudospin ladders. Then we move on to applications to chemistry. We'll start with rho vibrational spectra, which is a really nice application of quantum mechanics to an experimental observable system. There's a lot of interesting stuff, including selection rules, and you can understand a lot about the behavior in the spectra just by applying what we know about the harmonic oscillator and what we know about angular momentum. We have to generalize it to an anharmonic harmonic oscillator to get it correctly. And then we talk about the angular momentum and the spectra of an asymmetric top. This is a problem that I've always been bothered by the way in which it's been treated by most other textbooks. And I think the way that I do it here is a really clear and concise way of discussing how the asymmetric top works. We then go on to discuss the simplest molecule, the hydrogen molecule. That leads us into a more general theory called Hartree-Fock theory. From that, we describe how coupled cluster and unitary coupled cluster works. Coupled cluster is typically what people view as the gold standard for quantum chemistry calculations. It's an absolutely beautiful method. It is similar to doing a variational calculation, but it isn't actually a variational calculation. However, the whole calculation is done without ever actually finding the quantum state. And it's amazing the way in which it works, and it's really cool to learn how the chemists have put this together. And then we discuss unitary coupled cluster. Unlike regular coupled cluster, when you work with unitary coupled cluster, you do have to create the quantum state. Unitary coupled cluster is interesting to a lot of people because it is a technique that could be put onto a quantum computer, and many believe this will be an interesting application of quantum computing into chemistry. Next, we have a chapter on quantizing light. We start from Maxwell's equations, not in the differential form, but we show you a form that is relevant, that doesn't require using calculus. And then from that, we show where the harmonic oscillator comes from. It is not that the vibrating light is a harmonic oscillator that's oscillating back and forth. The harmonic oscillator actually comes from the fact that you can map the real part of the electric field onto a position coordinate and the imaginary part onto a momentum coordinate, and then the modulus squared of the electric field is just the sum of the squares of that position and momentum operator. So it looks like a harmonic oscillator Hamiltonian. And the energy is proportional to the square of the electric field, and so that's how this mapping to a harmonic oscillator works. It's really important if you're going to quantize light to understand that and not think of light as being some harmonic oscillators that are oscillating in some abstract fashion. Then we get to one of the things that I think is most important for anyone who studies quantum mechanics, knowing what a photon actually is. This goes far beyond what we like to say, which is it's a particle of light. You need to really understand the details. How do I actually measure a photon? How do I get single photon sensitivity to detectors? How do I create single photon light sources? And how do I know that I have a single photon light source? That requires something called the G2 measurement. And unless you understand what a G2 measurement is, you do not understand what a photon is. We then talk about how you detect photons with heterodyne and homodyne detection. This is required because the photon frequency is so fast it can't be directly measured when we're looking at optical light. We then extend our formalism to the Mach-Zehnder interferometer, which we've already looked at. And we also look at something called a Franzen interferometer, which is an incredibly cool device. It actually entangles particles in time as opposed to in space. And the idea of that is totally mind-boggling. Every time I look at it, I think it is remarkable and incredible that such a thing can work. And then finally, we talk about squeezed light and why squeezed light is so important for LIGO in helping LIGO be more sensitive and be able to search for black holes and neutron star mergers over a larger swath of the universe. Next up is a chapter on quantum simulation with trapped ions. This is my quantum computing chapter, although it's not exactly quantum computing, it's quantum simulation. We'll talk about the relationship between the two, and then we will discuss the phonons that you have in trapped ions. These are the vibrations of the phonons. If you remember the video that I showed you of the center of mass of the ions moving in an earlier video, that is exactly the structure that we're going to look at when we solve for the phonons for the trapped ions. We'll then look at how you develop a spin-dependent force, and then from that we'll show how you can create effective spin models. And then we'll discuss what was the initial plan with the quantum simulation, which is adiabatic state preparation, and we'll discuss why it doesn't exactly work, but it kind of works in these systems. And then we'll discuss more general models such as the Lipkin model versus the Dickey model, which are some more recent sets of problems that have been looked at with ion traps. Our next chapter is on decoherence and squeeze states. We look at mixed states and why you have to describe them by a density matrix. We look at what a quantum channel is, which is a way of mapping a density matrix into a density matrix as it evolves as a function of time. From that, we will look at what are called Krauss operators and how you construct a Lindblad master equation, which is an approximate way of looking at the time evolution of a density matrix. We then will study some physical systems such as Rabi oscillations or the Hahn spin echo experiment in magnetic resonance. And then we'll conclude with a chapter on the damped harmonic oscillator, and it's really nice to see how we can go from the pure quantum harmonic oscillator with no friction into a damped harmonic oscillator that has friction, although there are some surprises that occur when you think about damped motion in quantum mechanics, and we discuss some of that as well. Then we get to our final chapter. This is our chapter on measurement. It's very different from measurement chapters in most textbooks because our focus is on how you measure individual quanta. We look at entanglement and delayed choice experiments. We look at interaction-free measurements. We carefully discuss the concepts of uncertainty, complementarity, and wave function collapse or state collapse, and how they relate to single quanta measurements. And then we discuss what is the true measurement problem. In my belief, the way in which von Neumann constructs the measurement problem, that a quantum system becomes entangled with a classical device, is utter nonsense. There really are no actual measuring devices that work this way. It would be really cool if we had them, but they don't actually exist. And to spend a lot of time talking about measurement within that context when actual measurement devices don't work that way seems very silly to me. And the way that I describe it explains why that isn't really the right way of thinking about the problem, but why there still are issues in the measurement problem that need to be worked out, and what are some of the open questions that need to be addressed. Hey guys, let's do quantum right.